All right, in this video, we are going to look at 9 examples of sets together with a notion of addition and multiplication. And we're going to ask if they're fields, and if they're not fields, what properties are failed. Okay, so n, the natural numbers, which is the positive integers with plus and dot. So the failed property, this is not a field. What does it fail? Well, it fails a lot. Addition's associative, that's fine. Addition's commutative, that's fine. Addition, well, there's no identity because 0 is not an n. When we include 0, we subscript with the 0. There's no additive. Let me actually write it like this. It fails the additive identity. It fails the additive inverses because things like -1 don't exist. And I think that's all the additive axioms it fails. Let's see, multiplication is commutative and associative, so that's okay. I don't. There's a multiplicative identity, so that's okay. I think it fails multiplicative inverses, but it does behave nicely with respect to the distributive property. So I think that's it. Just fails these three. Is the integers a field? No. What does it fail? Let's see. I think all of the additive axioms are okay. There's no problem. I think the only thing that doesn't really make sense here is the ability to divide by non-zero integers. So this fails multiplicative inverses. All right, 2z. Is this a field? No. What does it fail? I think this fails. Let's see. We have additive inverses, right? Because if you're even, then your additive inverse is also even. All the regular properties hold because they hold in Z. I think this just fails to have a multiplicative identity, and it fails to have a multiplicative inverse to elements. But all the other things hold. Is Q with plus and dot a field? Well, addition's associative, it's commutative, there's a 0 fraction, it's 0 over 1. It has inverses, right? The inverse of a over b is negative a over b. So that's all okay. Is the multiplication associative? Yeah. Is it commutative? Yeah. Is there an identity? Yeah, it's 1. Can you divide by non-zero elements? Yeah, you can take the reciprocal fraction if your fraction is non-zero. So this is a field. And then, of course, there's a distributive property as well. Great. Is Z6 a field? I think you have, at this point, worked out the multiplication table for Z6, and you'll find that multiplicative inverses don't always exist. In particular, 2 inverse does, well, if we look at 2 in Z6, then, or 2 bar, then 2 bar B congruent to 1 mod 6 is not solvable. Because you can work out all the multiples of 2. There's 0, there's 2, there's 4, and that's it. You'll never multiply something with 2 and get something that's not 0, 2, or 4 mod 6. And so you'll never ever get 1 in particular, so it's not a field. So you don't have multiplicative inverses, but everything else is true. There's a 1, there's a 0. All of those other axioms are true, and you'll go in and you'll check some of these that we're going to do by hand. You'll actually check all of them. All right, so let's go on to the next one. Is Z5 with plus and dot a field? Well, again, with these Z mod M's, you kind of prove that arithmetic already holds. So the only question is with these guys is, can you divide? And 5 actually is prime, and you proved that if P is prime, then for any A not 0 in ZP, there exists an X in ZP, sorry, Z mod P, such that A times X is 1. So that weird exercise I gave you last week, what you were actually doing is you were showing that if P is prime, then you have multiplicative inverses for all non-zero elements. So is this a field? Well, 5 is prime, so multiplicative inverses exist for non-zero elements, great. And it has all the other properties as well. So this guy is a field. And to compare and contrast, the important thing here is that 5 was prime and 6 was not. All right, so is that a field? Yeah. In fact, Z mod P, sorry, there should be a mod here. Z mod P is always a field when P is prime. Okay, what about the real numbers? Well, yeah, it's the real numbers and the complex numbers. These are our models for how we define field, right? We need an addition. Addition should be commutative. We need a multiplication, and multiplication should be commutative, and all these properties. Can you divide by non-zero elements? Yeah. What else? Does the distributive property hold? Does plus and dot intertwine together? Yeah, of course. So R and C are both fields. Now this last guy here, I want to spend a little bit of time on because it's an interesting example. So M2R is going to be the collection of 2 by 2 matrices with coefficients in R. And we want to know if this is a field. Well, what properties does it have? I think multiplication of matrices, addition of matrices is associative. Its addition of matrices is commutative. Addition of matrices has a zero element. It's the zero matrix. Addition of matrices has inverses, negative of your matrix. What else? Addition of matrices. Oh, those are the four for addition of matrices. Now let's look at multiplication. Hang on. Multiplication, it fails commutativity. One second. It fails commutativity. Sorry about that. It fails to have inverses. Again, multiplicative inverses, because something like 0, 1, 0, 0 inverse does not exist. But it satisfies all of the other properties, I believe, right? Its distributive property holds. Addition, multiplication is associative. There's an identity matrix and so on. So I think it just fails these two.